So in this video, we're going to look at springs, and we're going to look at why the elastic potential energy stored in a stretched spring is not equal to the work done by the weight force or the change in GPE. So let's have a look at some basics of springs. So we should know already that the elastic potential energy is defined as the work done to stretch an object to an extension x from being unstretched. That's the definition of it. So we should know that this comes from the area under a force versus extension graph for a spring. So we've got the force versus extension graph for a spring there, and I've highlighted the area underneath it in green. So that area would be equal to half fx, and if f equals kx, that equals half kx squared. Now, you may not have seen before doing exactly the same thing using integration, which is a method of finding the area under a graph. So if we integrate force by the displacement in the direction of the force, which in this case is extension, we can substitute in kx for the force, and if we integrate that between the limits of 0 and x, so from unstretched to an extension x, we end up with half kx squared, and that is our elastic potential energy. And the reason we had to make a substitution in for the force is because force isn't a constant, so we can't just integrate at that stage. So that's our basics for this. So what we're going to do is we're going to apply some conservation of energy. So if we don't apply any external forces to the system, the work done by the weight force of the object plus the work done stretching the spring, or the change in elastic potential energy, should equal 0. So any GP lost by it moving downwards should be equal to elastic potential energy gained. That's what that expression essentially means. So we should find that the change in GPE is equal to half kx squared. So how are we going to actually investigate that? Well, we're going to actually plot a graph. So we're going to do, on the y-axis, we're going to do the work done by the weight force, or the change in GPE. And on the x-axis, we're going to put the extension of the spring. And that would mean the gradient was equal to half k there. So that's what I did. I did an experiment where I changed the weight force and measured the extension, and it gave this graph right here. So we've got work done on the y-axis and x squared on the x-axis. So we calculated work done by the weight force by doing the weight force times by the extension. That's the force times the displacement in the direction of the force. Extension I did by measuring the extended length and subtracting the original length of the spring. And my spring constant that I used was 25 newtons per meter. So that introduces some problems. So on the previous slide, we saw the gradient of this graph should be half k, but we can clearly see that the gradient is just equal to k, so something is not going right here. So the key question is, where have we gone wrong? Well, I can show you. Let me bring back an earlier slide. Just to make it really obvious, this is where it's gone wrong. You hopefully can't miss that. So when we apply the principle of conservation of mechanical energy, we say that if no external force is applied, and then some conditions. The problem is, in this scenario, we applied external forces in this system, which is why it didn't work. So there's a few different external forces that might have acted on here. So if you put the mass through the spring and just let it go and let it keep oscillating until it's settled, your system will be acted on by the external forces of air resistance and friction. And that accounts for the missing energy. So we saw from the graph that we should have twice as much elastic potential energy as we actually do. And the reason for that is because when we hook in the masses and release it, the system has some kinetic energy as well as elastic potential energy. And it's that kinetic energy that is dissipated by resistive forces. So when it settles at the equilibrium position, all the kinetic energy has been dissipated by resistive forces, which is why the work done by the weight force is not equal to the elastic potential energy at the equilibrium position. The other way you might have done this is that you held the mass until you found the equilibrium position, so you didn't even let it oscillate. And in that circumstances, you are applying an external force to the system, so you are dissipating the kinetic energy it would have gained. So both of these things mean that the expression of conservation of energy we used earlier was incorrect. So let's dig into that a little bit more. So to start with, the spring is completely in its normal state, so it's unstretched. So I put the mass through it and I release it, and what you'll see is that the system gains kinetic energy as well as elastic potential energy as it loses GPE. And actually, when it gets to the equilibrium position for the first time, where I've shown in red, it still actually has some kinetic energy, half mv squared, and it has elastic potential energy calculated using half kx squared. So now we're factoring in kinetic energy, the equation does work. So the reason, and what I'm going to do now is, from the starting position to this one, we've traveled a very short distance. So between these two stages, I'm going to ignore any work done against external forces because it'll be quite small. So at this position, the change in GP will be equal to the sum of elastic potential energy and kinetic energy there. So kinetic energy accounts for the extra energy we found on the graph earlier. So let's actually look what happens. So instead of me just describing it, let's see it. So on the left, I've got a video. So what I've done is the spring is unstretched and I've just put a mass through it, but I've not applied any force to the spring. So let's do that. So we can see that if we just put a mass in and then apply no external forces to it, we get an object oscillating like this. And to get it to stop and go to the equilibrium position, you can see I've applied an external force. So actually, the total energy stored in the spring is not equal to the work done by the weight force of the object, because I've done some work in the opposite direction, which is dissipating some of that energy. So what would have been kinetic energy has been dissipated to me in this case, because I slowed it down. If we play that again, we can see that the system ends up going much lower than the equilibrium position. So you can see it oscillates above and below the equilibrium position. So actually, at the point where it's at its lowest, that would be the point where the work done by the weight force is equal to the elastic potential energy right at the bottom there. And then as it moves upwards, some of that elastic potential energy is transferred back into GP and kinetic energy. And this is something you'll study in more detail later in the course. You'll study, it's called simple harmonic motion there. So just to diagram what I was talking about, the black line is where the mass starts. So, and the red line is the equilibrium position. So what happens is the mass, when it gets to the equilibrium position, is traveling at some speed. So it has both elastic potential energy and kinetic energy. And then what it does is it continues beyond it and becomes stationary on the bottom purple line. So at that point, the change in GPE will be equal to the change in EPE. And then it will come back up and go above that to a position above it, where again the speed is 0. But at that point, some of the elastic potential energy has been transferred into GPE because it's moved higher, and it will keep oscillating between those positions until air resistance has done enough work to reduce its kinetic energy to 0, and it settles at the equilibrium position with elastic potential energy half k x squared at that point. So that concludes this video looking at elastic potential energy. I hope you found that useful in terms of explaining what's going on in a system and why the work done by gravity is not equal to the elastic potential energy stored at the equilibrium position for a spring. If you have any questions, please feel free to ask. I'll try and get back to you as soon as I can. Just comment below the video and I'll see what I can do. Thank you for taking the time to watch.